All right, in Chapter 7, we're going to start talking about parameters and sampling distributions and how we can look at these parameters that are very difficult to figure out using some of our basic statistics. So a parameter, which we have spoken about before, remember a parameter is a characteristic of the whole population. So it's something that would hold for the entire population. So for example, you might say that 53% of all Americans love pizza. So that's something talking about all Americans. It's talking about the entire population if the entire population was American. So that would be an example of parameter. Now that would be very difficult to find because you would have to survey and sample the entire population of Americans, which is quite vast. Now remember, the opposite of that is a statistic, which is just a characteristic of the sample. So the sample is obviously much smaller. So an example of a statistic for the sample, you might say that 45% of people in Delaware, Ohio, love pizza. So it's something that's talking about a smaller group, which is a subsection of the population. Now, this might be a good representative sample of the population. This one's probably not. If I just ask everyone in Delaware whether they like pizza, that's probably not a good representation of the whole population. So there are lots of different parameters and statistics we have in statistics. Here are some examples of ones that we've looked at and we'll look at. So we have different symbols for parameters and for statistics for different things we try to measure. So for a mean, we say mu. This is the Greek symbol mu. This would be the average or the mean of the entire population. While x bar, x with the line over, is going to be the average of a sample of a smaller group from the population. Proportion, same as a percentage if you take it out of 1 versus 100. So the population parameter for a proportion is just p, and the statistic is p hat. We've also seen the standard deviation one. Standard deviation, we have sigma for the parameter, and we have s for the statistic. Now sometimes these are calculated the same, such as parameter or for mean and proportion. Standard deviation, if you recall, actually has different types of calculation. And then finally we have the correlation. So correlation, the parameter is called rho. It is this Greek looking kind of P symbol, that's rho. And the statistic is R, that thing we did back in Chapter 3. So we have lots of parameters and corresponding statistics, and we want to kind of see what the relationship is between these, because these parameters are very, very difficult to find because it's usually larger groups. Statistics are easier to find. So what is the relationship between these two? And that's what we're going to look at when we look at a sampling distribution. First thing we'll look at a couple examples, just trying to pick out what is the population and what's the sample and what kind of statistic and parameter we'll be looking for. So in this first one, it says, in a study of American teens, a sample of 200 teens yielded that 140 loved Snapchat. In this problem, what is the population, sample, and what would be the parameter of interest, and what statistic would be used? So our population in this case, who are we talking about if we wanted the entire group? So I would say the whole population is simply going to be American teens. It's going to be basically everyone in the population. Now the sample in this case is who did we talk to? Who did we actually survey for this? And those are the 200 teens that were in the sample. Now the 140 is how many of them said they love Snapchat, but that's not the entire sample. It's that entire group of 200. Now what would we be looking for a parameter? Now a parameter would be for the entire population. And since this is saying so many out of so many, it's not necessarily a mean, probably more likely a proportion. So the parameter, I would say, is the proportion of all American teens who love Snapchat. And as far as the statistic, that's going to be the proportion of the 200. And the proportion of the 200 who like Snapchat is going to be 0.70. Now, how did I get 0.70? Well, I got 0.70 because 140 divided by 200 is 0.70. If I want the actual symbol for that, I certainly can do that. I just jump down here and I can insert my little p hat because this is a sample proportion. So if I want to put p hat in there, we can say p hat equals 0.70. Now, is the parameter 0.70? It could be, but it certainly does not have to be. So all we know for sure in this problem is that 70% of the 200 love Snapchat. The actual parameter could be larger, it could be smaller, we just don't know. All right, let's look at this one down here. It says in a study of 450 American adults, they spend an average of 12.2 hours per week watching Netflix. In this problem, what's the population, sample, and what would be the parameter of interest, and what statistic would we use? So in general, I would say the population is everybody we want to know about. In this case, I would say that's American adults. The sample is how many people did we actually talk to from the population. In this case, it's the 450 American adults. Now, I'm not really sure how those 450 people were drawn from the population. Were they randomly selected? Were they just, conveniently selected? Who knows? But that would be our sample. Now, our parameter I would be interested in this case is I want to know the amount of time all American adults spend watching Netflix on average. So this is obviously a problem about the mean, and the parameter we actually want to know about, the population parameter, recall, is mu. So that is what we actually are trying to find. We're trying to find the average of all American adults, how long they watch Netflix every week. And that would be a hard thing to find. So what we're going to do is we're going to use the statistic, which we know. Statistics are much easier to find. And the statistic is going to be the mean time the 450 spend watching Netflix. And in this case, we know that is 12.2. Now, the statistic for the sample mean is going to be x bar. So we'll say x bar equals 12.2 hours. So, pretty easy to pick out what you're trying to find, what you have. But the trick is, we have this one sample of these 450 American adults, and it was 12.2. But the trick is, every sample is going to be different. It is very, very unlikely that you would sample repeated groups of 450 adults. So I take one group of 450, they say they watch an average 12.2. I take another group and they say they will do probably something else. The likelihood they would all be 12.2 is not very good. They'll all be something different. Just like if I was to pick a smaller group from the class and ask some question, it would always be a different answer, or somewhat of a different answer. They're definitely not the same. So this is one of the statistical phenomena we call as sampling variability. And this is something we have to try to work with carefully, because if I can figure out how all these samples are laid out, then I can actually figure out how they relate to these parameters, which is what we're actually trying to figure out. So sampling variability is just this phenomenon where we have samples pulled from a population. We'll have different statistics by random chance. And we're going to see how this works. Okay, we're going to see how this works. So as we pull more and more samples from the population, they're going to have different statistics each time. And based on that, we want to kind of see if we have these different ones, if we have these statistics that are different, is there a pattern to these statistics? And the good news is the answer is yes. So we're going to try a little experiment here. Now, in general, we would flip a coin 20 times and we'd see how many heads we got. And we could fill out this little chart, but in general, since we're going to just do this online, I'm just going to do this a bunch of times. So I'm going to flip a coin a bunch of times, and then I'm going to find the proportion of heads, okay? So down here in this table, I'm going to put proportion of heads that I get in 20 flips. So in general, if I got 10 out of 20 heads, then I would get that to be 0.5. If I got 11 out of 20 heads, I would get this to be 0.55. If I got 1 out of 20 heads, I would get 0.05. Now remember, when you flip a coin, we know the proportion of heads you should get. We know the parameter P equals 0.5 because 50% of the time you should get heads and 50% of the times you should get tails. So these all down here are going to be just little samples. So this right here, this 0.5, and all of these down here are little p hats. But the question is, what's going to happen when I do this over and over and over again? What's going to happen when I get all these little p hats? What kind of patterns will you see? Okay. So I'm going to jump over here to this website, and this website does a great job of pulling out a bunch of samples, and we can kind of see what patterns we see from these samples. Now, I'm going to go ahead and set the population proportion at 0.5 because we know that 50% are heads and 50% are not. And you can try this website if you want. I'll post it on Google Classroom. But you can go ahead and pick your sample size too. And the goal is we want to see what's going to happen when we start sampling. So let's just do one sample at first. So I'm going to do one sample. And this sample, it said I had 20 flips of the coin, and I got 9 heads and 11 failures. Now in this case, it's calling it success and failures. I could change that if I wanted to. I could call this. I could call a success a head, and I could call a failure a tail, just to make it a little more the same. So you see that we have in this case. Well, now we went 10 and 10. But if I do it again, the chances I get the same are not very good. So this one I got 13 out of 20. And you can see what I've done down here. This is my little dot plot down here. So I've got one p hat, one sample that was 0.5 and one sample that was 0.65. So imagine flipping your coin 20 times. One time you get 10 out of 20 and one time you got 13 out of 20. And I can do this over and over again. I'll just keep drawing samples, and they're just kind of all over the place. This is kind of showing our sampling variability. When you pull a sample from the population, their statistics are going to be different than the population. Only a couple of these are actually 0.5. Most of them actually look a lot bigger. Let's go ahead and ramp this up. Let's ramp and do 100 samples. So now if you do 100 samples, you can see most of them are still 0.5, the majority anyway, but there's a lot below, there's a lot above. You see there's a 0.2 down here, which is really, really small. And there's a 0.8 up here, which is really, really big. Let's draw 1,000 samples. So this is like we have 1,000 people in our class and we all do this. And so you see this. And let's draw 10,000 samples. And so now what you try to see is we do this over and over and over again. What you try to see is you actually see somewhat of a normal curve, a normal distribution. So this is a really, really important fact. When you draw samples over and over and over and over from the population, if you do this in theory infinitely many times, what you'll see is you'll see a somewhat bell curve kind of shape appear. And even more importantly, this is the most important thing of this whole section right now. If you look at the mean, so if I took the average of all these p hats, so I took all these p hats, all these little statistics, and I took the average of them, look what the mean is. It's 0.498. That's extremely, extremely close to my 0.5. So if you have a lot of samples, on average, those samples will be 0.5. Even though a lot of them won't be 0.5, on average, they will be 0.5.